This project aimed to show that not only can the performance of movement be classified by correctness, but the method of doing this is portable and general enough to allow for many different movements to be measured. Within this project, the goal was to be able to classify correct and incorrect form of a resistance exercise within a gym setting, therefore producing a system able to improve the safety and health within gyms and help reduce many injuries that can be suffered, such as lower back or knee pain. The system is able to determine if a video of a movement is performed correctly or not based on a learned dataset of videos. This learned dataset consists of videos of the movement being performed both correctly and incorrectly to give an accurate comparison between right and wrong form. To process a video, it is first passed through pose estimation using a convolutional neural network and heat maps. The CNN will predict the coordinates of each joint in 2D space, which is then further extrapolated and predicted into 3D space. For this project, VNect was used as it produces 3D coordinates rather than the two-dimensional output of most other pose estimation libraries. Pose estimation produces a time series of the coordinates of each joint position for each frame of the video. On screen is a visual representation of this time series of joint positions. These positions are translated into a time series of the angles for each joint. Using the angle rather than the absolute position of a joint introduces robustness into the system. It means that learning performed in the time series is independent of the position of a person within the frame and only concerns how the body is moving relative to itself, removing influences such as height. All learning and classification performed by the system is on joint angle time series, allowing the use of first nearest neighbor dynamic time warping to perform this task. This algorithm is very powerful when attempting to classify a time series due to comparing patterns of difference between a series rather than the absolute difference between them in Euclidean comparisons. The produced system runs through the command line interface. A model is trained on a directory of videos of a single repetition of the movement that is aimed to be trained on. This directory contains videos of both an incorrectly performed repetition and a correctly performed repetition. To call training, the shown command is input with arguments of a directory of video files and a name for the produced model. Using the VTSC executable, we'll first call the video to time series converter on any unconverted videos within the directory. Then these directories containing the time series of joint angles for each video will pass to the TS analysis Python component along with the model name to train into a single model file. This process of pose estimation on a video, then mapping the pose estimation to joint angles, takes about 13 seconds for each video, resulting in this directory of 67 videos taking about 15 minutes to train. The footage of the middle 13 minutes will be cut for brevity. After conversion to time series is complete, here it can be seen each CSV time series is read into the Python component and a model file is written to the directory with specified name. Classification is called in the same format and similar arguments as with training, with a model to perform comparison for classification and a video to be classified. The video to time series converter is run on the input video, and after the conversion, the resulting time series is passed off to TS analysis, where it will be compared against the model file to produce a single result of either correct or incorrect. A result of the split introduced into the system is that if an input video has already been run through the video to time series converter, the produced folder can be used separately in the learning component by calling TS analysis separately. This includes both directories of training data or single converted videos for classification. An unexpectedly proud part of this project is the compression factor found in converting a video of human movement into a time series of the joint angles within that movement. A frame from a video file of unbounded size will get compressed into a line of 14 numbers, one for each joint. This resulted in an average compression of 95% from an average video size of 2.4 megabytes to average CSV size of 11.7 kilobytes. The project achieved the main goals that were set out in the beginning and achieved a much higher accuracy than I thought was possible, given the losses in accuracy that were expected using many intermediaries from input of data to information used in the learning algorithms. The project was also very able to cope with many different types of movement, with 3 different movements all with tested accuracy of at least 65% and a mean accuracy between these movements of 77%. A highest accuracy of 87.5% reveals this method can be very accurate for this type of problem.